We are now live. Welcome everybody to our physics department colloquium. It is my great pleasure that we have with us today Professor Xiaoming Mao from the University of Michigan. Before I introduce her, before I tell you a little bit about her, I'll just remind you of the format here. Please keep your stay muted and use I'll monitor the chat and the raised hands during the talk. It's informal, so if you need to shout out a question, I think it's okay.
Yeah, I would like to welcome people to just interrupt and ask questions. That's actually easier for me.
Yes. And so Professor Mao comes to us from the University of Michigan. She got her PhD in 2008 from the University of Illinois at Urbana-Champaign. She worked with Paul Goldbart on what we call soft random solids. So think rubber, sponges, maybe fiber networks, systems that are elastic, but in which things are connected internally in a disordered way. And that turns out to produce interesting stress correlations that she studied in her thesis. She then went to the University of Pennsylvania and worked with Tom Lubensky, looking at the elasticity of these special lattices that she will surely tell us about during the talk, so I won't say too much about it. That field just exploded. So she kind of made some seminal contributions to there, but then that field really exploded when it was realized that some of these floppy edge states in these systems had a topological interpretation. And in the past, so while she's been at Michigan, Professor Mao has done a lot of really creative and interesting work on the theory of these materials, the different ways of describing them in the continuum limit and from direct studies of the microstructure. She's now running a large group at Michigan. She has 4 students and 3 postdocs, and they're working on topological mechanical materials. I just mentioned that one of her collaborators is our own Steve Craig in the chemistry department, who's trying to manufacture in the lab materials that will have some of the properties that Professor Mao has discovered are possible. So I'm really looking forward to hearing her tell us about this field, and let's welcome her. And we'll, if you'll share your screen now, we're ready to start.
Okay, thank you very much. So let me do slideshow. Okay, can everybody see the slide? Okay, great. Yeah, so thank you. So hello, everyone. It is my great pleasure to have this virtual visit today. I'm having a lot of fun talking to everyone. So I'd like to thank the organizers for giving me this opportunity. So today I'm going to talk to you about some recent work we have been doing along the lines of studying topological mechanics in aperiodic networks. So to start, I'd like to invite you to think very generally about biological systems versus engineered systems. And here I took this picture from Wikipedia, which compared the 2 sides across many length scales. So as you can see on the biology side, from the size of the DNA molecules to virus and the cells and the organisms, things are usually very messy and complex, in the sense that the structures are very disordered and the system operates out of equilibrium. And these structures are self-assembled and have interesting hierarchical structures in both the structure, geometry, and the dynamics. So things are very difficult to describe theoretically, typically. And on another hand, engineered systems are usually ordered, and we try to keep things simple, and there's usually one major length scale that controls the phenomena we see. So at a first sight, one may think that this is much better than this because things are more clear and under control. But on another hand, we know that biological systems are highly robust, and the plants and animals can adapt to environment that are not native to them. And then for engineered systems, it's very difficult to reach this level of robustness. So why biological systems are so robust, and what can we learn from that? Of course, this is a huge question in biology, and many people have been working on it. So for us as physicists, one interesting question we can think about in relation to this. Sorry, excuse me. So is this control bar blocking the title? No.
No, we don't see your control.
Okay, then that's fine. Yeah, it's only blocking it for me. Okay, so as a physicists, we can think about the mechanisms in physics that can give us robustness and think about how they relate to biology, right? So one familiar mechanism that can give us robustness in physics is attractors in phase space. For example, fixed points or limit cycles. So we know that in some dynamical systems, the dynamics is such that no matter where in the phase space you start with, or no matter what kind of perturbation you had over time, the system always evolves into certain states or certain sequence of states. And then as a result, it's very robust, right? So this is one possible mechanism. And there is another type of mechanism called topological protection, which is more studied more recently in condensed matter physics. So here the robustness comes from some kind of topological states, which are very robust against continuous deformations. So here I'm just using the simple example of a topological insulator, where the inside of the topological insulator and the outside, which is vacuum, belong to different topological states. So at the boundary between them, you necessarily have to completely destroy the insulating state and close the gap and have a metallic edge. So this metallic edge is very robust. Even if you have obstacles on the edge, the current can go around it because it is protected by the different topology on the inside and the outside. So this is a different mechanism that can give us robustness. Now it's interesting to think about whether these mechanisms are related to robust phenomena in biology. Right, so the connection on the left has actually been explored a lot in the literature. For example, many biological clocks have been shown to be limit cycles. But this connection on the right is much less explored, but may give us interesting discoveries in the future. So how topological protection may relate to the robustness you see in biological problems. So this is one theme that we have been very interested in my group in the past few years, and we are trying to understand this from different directions. So this is still a very challenging question, and we're trying to start from some simple questions first. And one of the starting points we took was to study and focus on topological edge floppy modes and the states of self-stress in aperiodic elastic networks. So the reason we chose this as a starting point is that these edge floppy modes and the states of self-stress have a big effect on the mechanical response of the material. And then it may have interesting relevance for biology and material science. So we would like to understand this as a general question. So even for this beginning question, it is still very challenging, because if you think about most existing theories of topological states, most of the time we start from some periodic lattice models, because periodic lattice models has the nice property of translational symmetry. And starting from there, you can have momentum conservation, and you will have nice concepts like the Brillouin zone and the winding numbers, right, which are necessary ingredients for many definitions for topological states. However, when you have disorder, you don't have these nice properties of translational invariance and the momentum conservation. So how do we study topological states in disordered or aperiodic systems? This is quite a challenging problem. But on another hand, we believe this is very important to understand, because in some sense, the practical value of topological protection is precisely that the phenomena you see is robust against the disorder. So it is useful to push these concepts forward to realize them in disordered problems. Okay, so with this, we can come to the outline of my talk today, where I will discuss briefly two recent work we have been doing along the lines of studying topological mechanics of periodic lattices. So here we studied it in disordered fiber networks and quasicrystals. So for both of these, I did this work in collaboration with my former postdoc, Di Zhou, and my former graduate student, Le Yu Zhang. Okay, so let's start by thinking about these fiber networks. So by fiber networks, we really refer to a group of materials which has the basic structures where you have fibers that are tied together by cross-linking points. And in this work, we are interested in exploring how geometric perturbation on this network, sometimes coming from active driving, can introduce topological edge floppy modes in these fiber networks. And then these edge modes will govern the local mechanical response. And then if we understand that, we will be able to program the functions in these materials. Okay, so before starting talking about the topological mechanics, I'd like to just take a little detour for a few minutes to give you a little bit of background about fiber networks themselves. So as we mentioned, the fiber network is a very simple concept, but it really captures the essential structure of many different types of materials you will encounter, including, for example, natural materials such as the cytoskeleton and the extracellular matrix, both of which are disordered fiber networks of biopolymers, and also many man-made materials such as felt and paper and the network of nanofibers. So as you can see, the length scale is very different for these different examples, and the chemical composition is very different, but they share some common essential structure of fibers, of disordered fiber networks, right? And we are interested in these materials not only because they are everywhere in our daily life as a material, but also they have very interesting mechanical properties. So for example, many of us know about this phenomena of strain stiffening in fiber network materials, where as you give the network a nonlinear strain, the elastic moduli can jump by more than an order of magnitude. So this is one interesting nonlinear elasticity behavior. And even if you stay in linear elasticity, the elasticity can be very sensitive to geometric parameters in the network, such as the density of crosslinks and the density of the fibers. And as you change these parameters, the elastic moduli can also jump by orders of magnitude. So these sensitive change of elasticity as you change some geometric parameters indicate that there may be some kind of underlying mechanical critical point that give you this sensitive response. So how do we understand this mechanical critical point? So to do that, let's start by thinking about a very simple minimal model of fiber networks. So we throw away the complicated macroscopic details and just think about fibers as thin elastic rods and the cross-linking points as hinges that connect these rods together. So I'd like to mention that by doing this, we're assuming that the thermal fluctuations can be ignored. So we are in the regime of persistence length greater than the mesh size of the network. And you can model these in an athermal way. So this applies to, for example, semi-flexible and stiff polymer networks and the fiber networks of macroscopic fibers. and not to flexible polymer networks. Okay, so when you make this simple assumption, you will immediately see that for each elastic rod, each of the fiber, it's much harder to stretch them than to bend them. So we are almost always in the limit of bending stiffness, much smaller than stretching stiffness for each of the fiber in this network. Okay, and then you can consider the limit of completely turning off the bending stiffness and turn this fiber network into a central force network. So the mapping is just simply that each of the cross-linking point turns into a mass point here, and each of the fiber segment turns into a linear spring that connects these points. So I just turn this into basically a bead and spring model. So central force really just means that the interaction between the two mass points only depend on the distance between them. Okay, so the mechanics in this simple limit has been studied for a long time and it really dates back to Maxwell. So from Maxwell's work, we know that a mechanical network is at the verge of instability when the degrees of freedom and the constraints balance with one another. So if we have too many degrees of freedom, we will have zero modes, which are ways to deform the network without changing any constraint. So it costs no elastic energy. And if we have too many constraints, we will have states of self-stress, which are ways to distribute stress on the network, where leaving all of the components in force balance. So it is only when these two numbers are equal, the system is in a very special mechanical critical state, where you have just enough constraints for all of the degrees of freedom. Okay, so then if you have a large central force network, you can write this equation as averaged quantities per particle, where the degrees of freedom is d as a point like a particle in d dimensions. And the number of constraints is the coordination number divided by 2. The coordination number is just the number of arms stemming out from one side. And each of the arm as a linear spring give you one constraint, but it's shared by the two neighbors. So it is divided by 2. And this equation is often written in the form of z equal to 2d, and is a pretty well-known equation in soft matter because it is the point where the jamming of frictionless spheres happens and where the rigidity population occurs on diluted lattices. Okay, so then this was basically the idea of this work we have done a while ago, trying to understand the linear elasticity phase diagram for fiber networks. So by studying some diluted lattice models, we extracted a phase diagram like this, where the horizontal axis is the bending versus stretching stiffness for each of the fibers. And the vertical axis is the connectivity of the network in terms of the coordination number. So in the limit of bending versus stretching goes to 0, you are in the central force, bead and spring model limit. And in this limit, the network only has rigidity above this central force as a static point, which is the rigidity population point of the lattice models we study. And above this point, the network has rigidity even if it just only has central force interactions. So the elastic moduli is going to be proportional to the stretching stiffness of the fibers. And it's large. And below this point, the network is connected, but it doesn't have rigidity in the central force limit. So it needs additional interactions such as bending stiffness of the fibers to give it an elastic moduli. So you only have elasticity when you turn on bending stiffness. So the shear modulus is going to be proportional to the bending stiffness of the fibers. So the elastic moduli is much smaller here in the bending dominated regime than in the stretching dominated regime. And then this is the connectivity percolation point. Below that, the network is not connected. So of course, it doesn't have elasticity. And in the middle, because of this critical point, you have a regime where stretching and bending are coupled and the elastic moduli depend on both. Okay, so this qualitatively explains in many materials why the elastic moduli can change by orders of magnitude as you change these geometric parameters, because it comes from a crossover from bending dominated behavior to stretching dominated behavior, where the stiffness is very different. Okay, so then what about the nonlinear behavior? So the nonlinear behavior has a similar geometric origin. So if you think about a network that is below the central force isostatic point, in the linear elasticity regime, it is very soft and has a lot of floppy modes. It cannot carry stress using the central force springs. Okay, but as you stretch it out to the nonlinear level, you are going to stretch out the zigzag lines in this fiber network and prepare central force chains that can carry stress. So there is a bending to stretching crossover as you go to nonlinear elasticity. So by studying various lattice models, we arrived at this three-dimensional phase diagram for the nonlinear elasticity of fiber networks, where this plane is the linear elasticity phase diagram that you have seen on the previous slide, and this axis is the nonlinear strain. So basically, as you start from a linear bending regime, which applies to most of the fiber network materials, and go up, you are going to prepare force chains, and the network has a transition from floppy to rigid elasticity, and eventually it crosses over to stretching dominated regime, and the elastic moduli can change a lot, okay, from this crossover. So this explains the strain stiffening for some of these polymeric materials in an athermal picture, and some other materials, depending on the type of fibers, could also have strain stiffening by stretching out thermal fluctuations. Okay, so there are different mechanisms that can give you strain stiffening. So anyway, to finish this part, I'd like to mention that we have also studied fracturing of these fiber network materials, and we saw that their fracturing process is very special. Basically, the crack nucleation that is typical for many brittle materials is completely avoided in these fiber networks because of this criticality in their rigidity. Okay, so more details is summarized in our paper here. Okay, so now let's come back to topological mechanics. So the motivating question we would like to understand by studying topological mechanics in these fiber networks is really trying to understand what is the nature of the floppy modes in fiber networks. So as we mentioned, most fiber networks are 4 coordinated at each cross-linking point, right? If each cross-links 2 fibers together, then the coordination number is 4. And on the boundary, when you have dangling ends like this, the coordination number is lower than 4. So on average, we are always in a regime that is bending dominated, because when the coordination number is below 4, it is below 2D in both two dimensions and the 3 dimensions. So we are almost always in the bending dominated regime. And there are a lot of floppy modes that only bend the fibers and do not stretch them. So what is the shape of these modes, and how do we understand their mechanical consequences? So to study that, we started from this so-called Mikado network model, which is a more general model than diluted lattices. So there is no underlying periodic lattice. The Mikado network is just constructed such that you throw a bunch of straight lines on the 2D plane and put down a cross-link whenever they cross. And then in the central force limit, if you just consider these as springs, you can do a Maxwell's counting and find that the number of zero modes is exactly equal to the number of fibers. So in fact, you can decompose all of the zero modes into the polling mode of each of the fibers. So here I'm showing you one example. You can pick an arbitrary fiber and pull it along its longitudinal direction. So here, the red arrows are the displacement vectors of the nodes, and the green arrows are the projection to the fiber you are pulling. So all of the red arrows are perpendicular to the crossing fibers, so that to linear order, they don't change the length of the crossing fibers. And all of the green arrows have the same length, so that you don't change the length of the fiber you're pulling. So as a result, it is a well-defined zero mode. And then, as you can see here, it is a bulk zero mode, right? In the sense that the green arrow always have the same magnitude from the edge of the network to the center. There is no decay. So it's more like a plane wave state. So in the beginning of the talk, I mentioned that we studied the topological edge floppy modes in these models. So how are they related to these bulk modes? So the relation comes out when you realize that these fiber networks are very much analogous to Maxwell lattices when they are in their critical states. So Maxwell lattices are defined as periodic lattices with this mechanical criticality condition of z equal to 2D. So here I'm showing you one example of a deformed Kagame lattice. So for Maxwell lattices, when they can be in different states where the zero mode distribute in different ways, but when they are in their critical states, namely the state that is at the boundary between different topological states, the zero modes penetrate infinitely deep into the bulk of the system, which is analogous to the zero modes you see here. Both of them are bulk zero modes. Okay, and then if you're familiar with the so-called Maxwell-Caledon index theorem, you can see that this comes from the fact that you have straight lines of bands in this network that give you states of self-stress under periodic boundary condition, and then you must have zero modes under periodic boundary condition, which are bulk zero modes. But if you're not familiar with this, that's totally fine. So geometrically, what you need to see is that the existence of these bulk zero modes come from the fact that you have these straight lines. So in fact, it is known that in Maxwell lattices, when you break up these straight lines, you can push this plane wave like zero mode to exponentially localized on the edge. So here, there is this interesting concept of topological polarization that has been introduced in this seminal paper by Kay and Lubinsky. They show that as you break up these straight lines and zigzag in different ways, you can either make the mode to be localized on the bottom or localized on the top. And this is a topologically protected phenomena, so that you can have small disorder in the network, and this localization is a very robust phenomenon. Okay, so in this more recent paper, we took this concept and we show that you can actually make metamaterials. It's of the same material, but this network has a very nice property that it has an intrinsic soft strain that you can reconfigure it between these different states. So the reconfiguration is basically just pulling this network out, and it doesn't cost elastic energy because you're just changing the angles at these hinges. You don't change the length of any bond. And by doing this, you can transform the lattice between different topological states. And the consequence is actually very easy to see. So in this state, you have exponentially localized zero mode on the bottom edge. And when you push it, the edge can accommodate this deformation by the zero mode. So it appears very soft here. And then if you are in the topologically polarized state, all of the zero modes are exponentially localized on the top, leaving the bottom edge to be rigid. And here, now if you push it, the whole thing slides instead of deform. And this is quite surprising to us from the perspective of thinking we build this using connects, and all of these points are free hinges. You would normally not expect to have a rigid edge from a whole bunch of free hinges, but it really comes from the effect of topological polarization. And also you can see that this is a very robust phenomenon. We build this using toys with a lot of imperfection, but the effect is very easy to realize. Okay, so this was some ideas we're currently still working on to make transformable topological mechanical metamaterials that can be tuned between many different mechanical states. Okay, so coming back to fiber networks. So we know that this can happen in periodic lattices, right? When you break the straight lines, you can push and manipulate this zero mode to localize at different places in the network. And the effect will, you can use this effect to program soft spots and hard spots in a material, which could potentially be very useful. Right? So then we were wondering, can we do the similar thing in fiber networks? So in particular here in the periodic lattice, what we did to transform it is really to follow a bulk zero strain of the network where you can strain the whole thing without costing elastic energy. So we try to do the same thing here to shift this fiber along its bulk zero mode. So basically you follow this bulk zero mode that we just talked about. And then locally, the geometry is such that the fiber you're pulling becomes zigzagged. And then you can define a new ground state out of this. Because I'm following a zero mode, the stress that is generated is higher order. We ignore that stress and we define a new ground state that is the so-called modified Mikado network. And then we were wondering what is the zero mode in the modified Mikado network. So we calculated the zero mode and find that, interestingly, it also becomes exponentially localized. So with a little bit of change of geometry, previously it is a plane wave-like mode. And by changing the geometry a little bit, it becomes exponentially localized. And in particular, when you pull the fiber to the right, it always localizes at the tail of the fiber. And we obtained this result using an exact transfer matrix method, which I don't want to go into detail, but basically it is just depending on the local geometry at each cross-linking point, depending on the crossing angle of this fiber you're pulling with the crossing fibers and how it zigzags at each cross-linking point. You can calculate whether the mode decays or grows at the cross-linking point. And then you can show that if you pull the fiber to the right, the geometry is consistently such that it decays from left to right. And if you're interested, you can look at our paper where we have a rigorous proof of the disorder averaged decay rate in this network. And we also designed numerical simulations to test that this effect is still there when you have bending stiffness. So remember, in all of the calculation here, we ignore the bending stiffness. But if you add back bending stiffness, numerically, you can show that the the asymmetric stiffness is very robust. And we also talk about how do you define a topological index in the disordered case. Okay, so then to finish this part, I would like to just briefly talk about like a possible realistic situation such mode can be excited. So one interesting case is to have a network with some active driving. For example, when you have molecular motors on this network, such as a molecular motor that locally contracts sections of this network. So when you contract, obviously, it is going to take advantage of this bulk zero mode and contract the fibers like this. And then from what we analyzed, you are going to generate opposite topological polarization on the left-hand side and the right-hand side of the motors, and prepare a domain wall that separates them. And then when you calculate the mode, you're going to get something like this, where the mode first exponentially decays and then exponentially grows on the network. Okay, and then depending on whether you have a contracting motor or an expanding motor, you will have localized hard spots and soft spots distributed in different ways in this fiber network, which may be an effect that could be observed. And another interesting effect is that if you use some contraction to generate a mode such, of this shape, where it decays and then grows, then interestingly, this system can act as a mechanical amplifier, because if you have a small mechanical signal at the center of the network, it can excite this mode, and this mode will grow as you go out to the edge of the network, and then you will have large output on the outside. And this acts as an interesting mechanical amplifying mechanism and may have interesting consequences in some biological problems, like we mentioned earlier in the talk. So there is a simple video, which is a confocal video of cells in extracellular matrix. Here, I think it's collagen gel. And as you can see in the video, the orange dots are the cells. And there is a lot of interesting active interaction where the cells pull on the collagen fiber network, and it deforms this network and possibly excite modes like this. And then the cells will take a ride on this fiber network, and the cells at different locations can communicate with one another. And it will be very interesting to explore the effect of these topological modes in some active processes that is happening in these active, in these biological polymer network systems. Okay, so that's basically the part on fiber networks, where we explore how to push the concept of topological modes to disordered fiber networks and how that might relate to biological problems. So in the next part of my talk, I would like to discuss a different project we have done in this general direction of pushing topological mechanics to quasi-crystalline structures. Okay, so let me change into the pointer. Okay. So we know that quasicrystals are very special structures which are aperiodic, but they still have long-range order. So interestingly, this long-range order is very different from the long-range order in crystals. So it will be interesting to understand how does this long-range order interplay with topological states. So this was basically the motivation that that motivated us to look at topological mechanics in quasi-crystalline structures. So we started from some familiar examples, such as the Penrose tiling. So the Penrose tiling is one example of a quasi-crystalline structure where you have an aperiodic tiling of the two-dimensional space using two types of quadrilaterals. And it can be shown that if you use these two types of quadrilaterals to tile the plane, you cannot tile it periodically. You can only tile it in aperiodic ways. Okay, so when you look at this network, you will see that the coordination number can range anywhere from 3 to 10, right? So it's not a z equal to 4 network. But interestingly, because all of the faces are four-sided, when you do a Maxwell's counting, you will see that the average coordination number, if you have a large tiling, it's always exactly at 4. So again, this is a Maxwell network. Then we were very interested in understanding what is the mechanical property of this tiling as a quasi-crystalline structure. So for example, the first question we can answer is, what are the zero modes, right? So it turns out that it's pretty easy to construct zero modes in parallelogram tilings. So if all of the quadrilaterals are parallelograms, you can construct zero modes like this, because you can always identify stripes of parallelograms that share parallel edges with one another. And for each stripe you can identify, you can construct a zero mode where you just shift one side of the edge relative to the other side. And obviously this is a bulk zero mode. The amplitude doesn't change from the edge to the bulk. Okay, so then again, we are interested in understanding what happens if we change the geometry a little bit. Is there a topological polarization that can be used to characterize the polarization of zero modes in these tiling geometries? So again, the motivation is that if we know how to program the mechanical property, if we know how to program the zero modes and the states of self-stress in these tilings, then we again will be able to program mechanical response and the functions. Okay, so it might be tempting to say that we just follow the same route as in the fiber networks and in the periodic lattices. We just follow this bulk zero mode and see if that is going to prepare the system automatically into a polarized state. It turns out to not work here, because if you just follow this bulk zero mode, every parallelogram stays as a parallelogram, right? You just tilt all of these edges, and the bulk zero mode stay as a bulk zero mode to nonlinear level. So it turns out that the topological polarization in these tilings can be constructed in a very different way, but gave us a lot of interesting new physics. So in order to discuss that, let me first spend a few minutes to talk about this concept of reciprocal diagrams, which again was proposed by Maxwell. So this concept comes from the concept of dual graph in graph theory. So you know that in graph theory, when you have two different graphs, they could have a relation called the duality, such that the node in graph A maps into the faces in graph B, and the faces in A map into nodes in B. And then each edge in A and each edge in B has a one-to-one correspondence. Okay, so the Maxwell reciprocal diagrams means that you have two mechanical networks that are not only dual graphs of one another, but their geometry is also related in a way that one edge in the first mechanical network with the corresponding edge in the other mechanical network are perpendicular to one another. So if this geometric condition is also met, then these two mechanical networks are reciprocal diagrams to one another. And this concept is actually very useful to us because the fiber networks and the quadrilateral tilings are reciprocal to one another. So this is in fact very much related to a method called the generalized dual method that has been proposed to generate quasi-crystalline tilings with arbitrary rotational symmetry. And it was first proposed in this beautiful paper by Josh and the collaborators. So here, as you can see, this quadrilateral tiling and this fiber network has this duality relation with one another. For example, if you look at this parallelogram in the quadrilateral tiling with a blue dot, it maps into this node in the fiber network. And the four edges that surround this face maps into the four edges that connect to this node. And each of the edge here has a perpendicular each of the edge here is perpendicular to the corresponding edge here. So they map to one another in a way that here every face is four coordinated, and here every face is surrounded by four edges, and here every node is connected to four edges. Okay, so you can check the correspondence on the two sides. Okay, so this is relevant for topological mechanics because if you know that two mechanical networks are reciprocal diagrams of one another, then immediately their mechanical properties are intimately related to one another. So to our knowledge, it was first shown in this paper here that if you have two mechanical networks that are reciprocal, then the states of self-stress in one maps to the zero modes in the other, and the zero modes in this one maps to the state of self-stress in the other. So this is a very interesting relation mechanically, and particularly useful because this tells us if you know how to topologically polarize one of the network, for example, the fiber network, which we know how to do it from our previous result, then if you do the corresponding geometric change on the quadrilateral tiling, then the other one also becomes topologically polarized. The reason is that there is a one-to-one correspondence between zero modes and the states of self-stress on the two sides. When the fiber network becomes topologically polarized, that means the zero modes are localized on one side and the states of self-stress are localized on the other side. And then from this one-to-one correspondence, you know that then in the corresponding quadrilateral tiling, the zero modes will be localized on this side and the states of self-stress will be localized on the other side. So they are always polarized in opposite ways when you look at these reciprocal diagrams. Okay, so this is basically the idea for us to study topological mechanics in these quadrilateral tilings. So here I would like to just spend a few minutes to talk a little bit about how to prove this theorem, which I think might be useful for other soft matter problems too. Okay, so just in like a 2 minutes proof, if you consider a pair of reciprocal diagrams, here I'm showing you a very simple example. Each face here mapping to a node here, and each edge has a corresponding edge. So here I labeled them for your convenience. If you focus at one node here, it maps into a face here. This node is connecting to three edges, 7, 1, and 12. They map into edges that surround this face. And the condition that such a correspondence exists is really the same condition as having a state of self-stress on this network. So it is actually pretty easy to see. So a state of self-stress means that you can put a stress on the bonds. For example, compressions on all of the green bonds and tension on all of the red bonds, and everything is in force balance. So when you have such a state of self-stress, that means that you can write vector forces that are along 7 and along 1 and along 12, and they add up to 0, right? So then that tells you can construct a polygon that comes from all of the edges connecting to this node, and that becomes the face here. So when you have a state of self-stress on one network, you can use that to construct its reciprocal diagram. So having a reciprocal diagram is the same as having a state of self-stress, and this is a mutual relation on the two sides. Okay, so I'd like to just mention that having the definition of this reciprocal diagram has actually been used a lot in soft matter, for example, to study jammed packings and frictional jamming and cells in epithelial sheets. So the idea here is basically that if you have a structure that is jammed, or it has mechanical stability and can carry stress, then it must have at least one state of self-stress. Then there must exist a reciprocal diagram, which is often called force tilings or force networks. So you can construct the geometry in the reciprocal space and then do the statistical mechanics problem in the reciprocal space, which may give us interesting information that was not available in real space. So there's a lot of interesting questions one can explore there. Okay, so coming back to the topological mechanics problem, you can show that when a pair of mechanical networks are reciprocal to one another, there is a one-to-one correspondence between their zero modes and the state of self-stress. So it's basically a proof like this, but I don't want to go into too much detail. So anyway, you can work out the Maxwell relation. And here I'm just including one example where you can draw such reciprocal diagrams for every Maxwell network, where you can show that two Maxwell lattices, when they are reciprocal to one another and they become topologically polarized, they must polarize in opposite ways, like what we described. Okay, so now let's come back to the quasicrystalline tilings and the fiber network. So as we mentioned, we know how to geometrically polarize a fiber network. So we can do the corresponding geometric change to the tiling, which means to rotate each of the bond in a little bit in its direction. And then previously, when we have this zero mode of shifting at each strip, it becomes an exponentially localized mode, as you see here. So we can do this consistently over the whole network. And as you can see here, we can make a Penrose tiling become topologically polarized in the sense that the zero modes are all focused on certain directions of this network, leaving the opposite directions to be rigid, like what you saw in the video that we demonstrate. And one particularly interesting phenomena here is that because this structure has long-range quasi-crystalline order, not like the fully disordered fiber network, here, when you try to characterize the topological polarization of this whole structure, you can see that you can define a bulk topological invariant that has quasi-crystalline rotational symmetry and is not limited to crystallographic group, and that you can achieve some interesting phenomena that was not available in crystals. And similarly, you can also show that when you polarize this tiling, the stiffness at the edges can become orders of magnitude different. And like we mentioned, because of this arbitrary rotational order, you can design devices that has arbitrary shape for example, waveguide or stress focusing device using the concept of topologically protected zero modes or state of self-stress. And you can start from the arbitrary shape you want and design the quasi-crystalline tiling that has these symmetry directions. Okay, so with that, I would like to summarize. we studied the topological mechanics in aperiodic mechanical networks, in particular in fiber networks and the quasi-crystalline tilings, which are mechanically due to one another. And we can study topological floppy modes and the states of self-stress, which we can use to program mechanical response in these materials. Okay, so thank you for your attention.
Thank you for a lovely talk. You couldn't have put together a set of topics that resonates better with me. I love all these all these geometric driven elastic effects. Our standard procedure at this point is to give graduate students an opportunity to ask questions before everybody else jumps in. So are there any graduate students who would like to speak up? I'll give you a moment. No? Of course, undergraduate students are welcome also. Thanks, Ronan, for clarifying that. Well, let's open it up to general audience questions from anybody. I will start out then. I mean, I have lots of questions, but I'll start by just asking, where do we stand now in the fabrication of materials that will exhibit these kinds of effects on scales that people think are useful, at whatever those scales might be, whether it's you know, civil engineering scales or subcellular scales. Where do you see the most interesting possibilities there?
Mm-hmm. Yeah, that's a very useful question to think about. So as you can see, it is pretty easy to make materials at this macroscopic scale to demonstrate this property. So we have been working with groups to try to demonstrate this at a smaller scale, and it sort of works. So we have been collaborating with Shu Yang's group at Penn, and she made using lithography's techniques. She made lattices that are sort of, the whole thing is centimeter scale, and then the hinges are like somewhere around the 100 micron. And then at that scale, things are quite delicate. And one thing we were able to do is to characterize wave field in that material. And it turns out that we can actually see the edge mode. So we're actually working on a paper on that. And but to make it more practical is still challenging. Like if you want a material that appears to be continuum, at least you don't see the holes, right? And still has this property. We are working on various ways to attempt to do that, but we haven't got there yet. Yeah. And we're also trying to push in the other direction to try to build a larger and larger scales for problems like architecture and space structures. And that is also at the sort of the proposal scale, proposal stage. Yeah. But yeah, it's good to think about this. Yeah.
I was curious about the networks of the motors, of course, coming from the biological point of view. So and that involves dynamics. So if you have a network in water, of course, or in a fluid, you have to worry about Poisson ratio and compressibility, right? And I guess that would change the at least the time-dependent response of the material when you think about rigidification or softening. Now, if you have motors, you have to also worry about scale, the distance scale. So you can have local effects where you get free draining and still have large-scale volume conservation. And sort of how does that play into these say signal transmission games when you have force transmission in a cell, for example? So.
Yeah, that's a great question too. So we haven't thought about that yet. So the picture I draw here is mainly a quasi-static picture. So you imagine that you just reduce the length of one segment here and ask what is the equilibrium configuration. And then the equilibrium configuration has this property. But if you consider in a dynamic setup, that will be very interesting to see dynamically you excite this mode. And this is indeed a very low frequency mode. So as you excite it, it actually will take quite some time to equilibrate, and then it interplays with the hydrodynamics, like you mentioned. Right, that's interesting. Yeah.
So this picture intrigues me too. I'm not quite sure I understand how you prepare this state. So, you start with straight fibers everywhere, and then you pull one so that it's got some fluctuations in it, and you kind of use that as your new equilibrium configuration.
Yeah, that's right.
So does that mean you had to make a very particular fiber network that just has this one fiber that's has this structure to it? If all of them have that kind of structure, if they're just sort of all of them have these fluctuations, does that destroy the floppy modes, or does it make more of them?
So I think if you don't pull too many of them, if you pull everybody, then you just translate the whole thing, right? If you don't pull too many of them, this effect will stay. I think I actually have on my backup slide.
But they're all getting pulled in different directions.
So. Yeah, you can pull them in different directions. So here is a demonstration of two fibers being pulled. The red one pulled like this, and the blue one pulled like this. And you can see the localization of the mode on each of them.
And they don't interact?
They interact a little bit, but to leading order, it is okay, because the way this works is through this transfer matrix, which exactly diagonalizes when everything is straight. So this transfer matrix tells you that if you have two displacement coming in, you can calculate the two displacement going out, right? So if these both fibers are straight, they don't talk to each other. You just have a diagonal matrix actually, and the bending of the fiber is a first order perturbation to that. So as long as you don't pull too many of them, at most sites you can still apply the geometric rules of the mode shape we calculated, then you still have this localization.
Well, I don't want to monopolize the conversation here. Are there other people? Well, it's 4:30, so if there are no other questions, let's thank Professor Mao again for a nice talk. Our next colloquium will be, I believe it's April 14th, 2 weeks from today, by Kwangji Kim, who is an accelerator beam physicist. Ying Wu will be the host. So I hope I'll see you here again in 2 weeks. Thanks very much.
Thank you.
Thanks for coming.
We'll for anybody who wants to sort of hang on for a little while, we have a little bit of time to just stay here. I'll stop the recording now.